Hello, class. For today's lesson is about from roots to real numbers, understanding rational and irrational numbers. And here are the learning targets. 1. I can identify irrational numbers. And I can tell the difference between rational and irrational numbers using numerical examples. In our last lesson, you learned that some square and cube roots are perfect, like the square root of 25, which is equal to positive and negative 5, and the cube root of 27, which is equal to 3. While others are not perfect, like square root of 2, cube root of 2, square root of 3, cube root of 5, and other numbers. These non-perfect roots are example of irrational numbers. Which leads us to today's lesson. In our previous topics regarding rational numbers, these are numbers that can be written as a fraction of two integers where the denominator is not 0. So you could write it as P over Q or A over B. Again, as long as your denominator should not be 0, which could lead to being undefined or it could be indeterminate given the situation. Now, since it can be turned into fractions, so we have here examples. We have 3 over 4, which is equal to 0.75 if we are to convert this into decimal. As you can see, it ends. So we just only have 2 digits on the decimal side here. Another thing, we have 7 over 2, which is equal to 3.5. So same thing with the first example. The number just ends. It is definite. However, if we are to have an example here, last one would be 1/3, which is equal to 0.333, or the number doesn't end, it is infinite, but at the same time, we know that the number here is just the same that goes on. So this one here is also a rational number. Directly to decimal. So if you also have, for example, 0.11221122, and we see that the pattern is there despite being infinite in the decimal part, this is also an example of a rational number. This one here, the 0.1122 that goes forever, is again what we called non-terminating. And examples like these, the 0.75, 3.5 are terminating numbers or examples. This one is also non-terminating. And yeah, that's it for a recap with regard to rational numbers. And to our main topic today about irrational numbers, these are numbers that cannot be written as a fraction of two integers. Their decimal form goes on forever and does not repeat, unlike with rational numbers. And these come often from non-perfect square roots or even cube roots and other index or nth roots and special constants. So square roots, cube roots to add, or other nth roots. Now, once again, if you remember the perfect squares and perfect cubes, so you have the for perfect square, you have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100, and other numbers. We also have, for the perfect cubes, let's just have 5, 1, 8, 27, 64, and 125. Again, these are perfect squares. And perfect cubes. So when we talk about irrational numbers, with regard to perfect squares or square roots, so assuming we have here a number line or an order. So we have here the square root of 1, square root of 2, square root of 3, square root of 4, and the list goes on. Now we know that the square root of 1 is 1. The square root of 4 is 2. So basically, in the square root section, so all numbers that are not perfect squares inside a square root sign are all irrational numbers, like square root of 2, square root of 3, square root of 5, and other numbers between square root of 4 and square root of 9. So again, if we are dealing with square root, okay, if we're dealing with the square root sign, and if the number, or what we call radicand, okay, again, if you are dealing with square root here, the symbol, and if we're dealing with, if a square root has a radicand, which is the number inside the square root, is not a perfect square, automatically it is an irrational number. So if we are to estimate the value of the square root of 2, so the square root of 2 has a value of 1.414213, and the list of numbers going to infinity goes on. So as you can see, there is no pattern here. So after 4, 1, 4, to make it rational, we could be expecting that the next number should be 1. So the pattern of 4141 is what we're looking for if you are dealing with rational numbers. However, again, going back to the definition of irrational numbers, so we have here numbers that cannot be written as a fraction, or if it is in decimal form, the number goes on forever and does not repeat. So yeah, that's it. Now let's talk about irrational numbers with regard to cube roots. So we have here cube root of 1 is 1, and the next perfect cube is 8. So we have cube root of 8, in which the value of this one is 2. So again, if we are dealing with a cube root and the number inside that radical is not a perfect cube, automatically all the numbers in between cube roots of a perfect cube, like this, the cube root of 1 and cube root of 8, are irrational numbers. So which means we have here for cube root of 2, cube root of 3, okay, up until cube root of 7. These numbers in between a cube root of a perfect cubed are all irrational numbers. So we also have, if we put another number, so you have cube root of 9, and the next cube root is 1, 8, 27, so cube root of 27. So all numbers in between cube root of 8 and cube root of 27 are all irrational numbers as well. So if we take into consideration here, we have the cube root of 6. If this is in decimal form, this is like 1.817 12 0.05 dot dot dot. So again, it goes to forever, but as you can see, there is no pattern actually with 8171205. So yeah, there's no pattern actually. So based, and as you can see, one here just repeated. So yeah, there's no pattern given or that is visible. So that's how irrational numbers work, especially when we deal with decimals. Now here are some 3 popular irrational number symbols. Okay. Irrational number symbols. Okay, so when we were in elementary, this one is the most popular. So we have this, the pi. Okay, so this is the ratio of a circle's circumference to its diameter. So for pi, we know that the approximate value for this is 3.14. But to write the complete set of numbers for this, it goes to infinity and there's actually no pattern. So if you write sum of the numbers, you have 3.1415926, and yeah, still there's no pattern, because again, if there is a pattern, if we base it on 1 4, then the next number is 1. We should be expecting 4 to be here and not 5. Another popular symbol, we have E. I don't know if you're familiar with this, but as you can see in the calculator, to the pi as well, they are just adjacent to each other. Actually, they are in the same, what do you call this? As, not symbol, the term is not symbol, but to the part in which you click in the on the calculator. So it's actually there. Now this is called Euler's number, or constant. Now this is the base of the natural logarithm. Now for the approximate value for this, I usually use this number to certain problems, is 2.72. However, to list some of its numbers, this is 2.718218 18 dot dot dot, and yeah, the number goes on to forever as well. And last, although I'm not sure if this is the last popular irrational number symbol, but last one would be the phi. So it looks like this. It looks like a 0 being tilted with a, what do you call this? A slash symbol. Yeah, it's a combination of those. Aside from this symbol, we could also use this. I'm not sure how to perfectly draw this. Wait, let me try. Something like this. Anyway, this is spelled as this one, phi, with an H. And for the approximate value for this one, would be 1.62. But to write some of the numbers for this is 1.61803339 dot dot dot. And similar thing to here, the pi Euler's number as well.